The next speaker is Jaime Mata-Falcon from ETH Zurich. He will talk about some example of large-scale projects with a presentation entitled Digital Fabrication of Concrete Structures, a Collaborative Approach. Dr. Jaime Mata-Falcon is a Senior Assistant at the Chair of Concrete Structures and Bridge Design of ETH in Zurich, where he joined as a postdoctoral researcher in 2015. In April 2016, Jaime Mata-Falcon joined the Swiss National Center of Competence Research for Digital Fabrication to address the structural integrity of the reinforced concrete technologies. So now we will hear about a new perspective, so the real perspective of structural design related to full-scale applications. Thanks and welcome, Jaime.
Thank you very much, Constantino, for the presentation and for organizing this interesting event. Good afternoon to everybody. So I will present this a bit more structural engineering perspective and the collaborative approach that we have we have at ETH, where I think we have several groups working together. So personally, I'm not working, for example, in material science as the other presenters in this session. Okay, so this is the outline of my presentation, and the last 3 points. I would like to introduce a bit of the research that we have been doing at ETH Zurich in the last 5 years. But first, I think it's important to give a bit my personal opinion of what are the potentials and challenges of digital fabrication in regards to, I think, structural engineering. I think, well, the motivation for digital fabrication should be to construct in a linear way. And I think there is, I have to admit, I think that concrete construction is close to 10% of the total CO2 emissions. So then I think we have a huge pressure to improve the environmental performance of construction and concrete construction in particular. But I think we have to indicate that I think formwork, when we try to optimize elements to do more custom designs, then I think the cost of formwork and also the material consumption is huge. For example, you can see in these pictures, this is the Rolex Center at EPF Lausanne. It's this cell structure, and this was a tailor-made formwork that after construction is a mountain of waste. So then we have a bit of a contradiction. I think we try to build more efficient structures, but then if the formwork is not properly solved, so then maybe it's not a good approach, I think, to do this optimization. And there is what digital fabrication offers: customization at not much extra cost or material consumption. I think this is the main goal of digital fabrication, which could enable us to use structurally optimized shapes and achieve our goal of having a linear construction. I think for concrete structures, this means that either we build without formwork. This is what you have seen in the previous presentations, I think, with 3D concrete printing. I think there are also some spraying approaches to do this. But I would like to point out that in digital fabrication, we can also have processes in which we use a non-conventional formwork. And I think this does not gather a lot of research attention, but I think there could be high impact on these other technologies. But okay, this is very interesting, but we face also a lot of challenges in digital fabrication. So I think it's difficult to be competitive at the moment. And I think we have to admit that also that conventional construction is in many cases very efficient. Here you can see in the bottom part some examples of hollow core slabs that contain insulation or in situ grid slabs. I think we have openings for installations, or I think bridge construction. It's already very efficient. So I think we can improve, but I think it's not that easy. I think other point that is maybe not helping us at the moment is that the most digital fabrication concrete mixes has much more cement and much more clinker into it, so they have more environmental impact than conventional concrete. So then to have a benefit, we should really reduce a lot the amount of concrete we use, or improve our concrete mixes. That this is something to be done. Then I think the integration of reinforcement has been already indicated by, I think, other people. I think at the moment, I think we have hardly ever no technology that can integrate, I think, maybe reinforcement in the amounts required by standard. There are many, I think, applications in which we have just unreinforced concrete. So then this cannot be considered a concrete structure. I think we are more competing with masonry structures that maybe are more efficient to build, like simple houses. Then even in the case that we can have this form freedom allowed by the technology, in the case of, especially in the case of housing, we have other requirements for geometric simplicity. So this might be also a limitation for the optimization in digital fabrication. Then the design philosophy is very important. I think in the next presentation, Fritz Boss will show a bit of what is the process of design by testing. But I think in my personal opinion is that research should focus in developing technologies, I think, to build in a digital manner concrete structures that behave similarly as conventionally built structures. Because if we deviate a lot and its laboratory or its concrete mix deviates in a different way, I think it's super difficult to reach some standardization, or to be able to design structures in the way we do conventional structures. So we don't need to do our prototype testing each time. And then other important thing is not in the fabrication side, but I think if we are talking about customization, so we need to talk also of new digital design tools to be able to handle the customization in an efficient way. And then last but not least, if we want to reduce this 8 to 10% CO2 emissions caused by the concrete industry, I think we should think a bit worldwide. It's a fact that at the moment, I think we are in general in high-tech solutions that might not be applicable in most of the constructions over the world. So these are challenges, but I think this is an interesting field of research. And I think we can really solve the challenges if we do some, I think, long-term interdisciplinary research into it. And I think this is a bit the approach that we are trying to have in Switzerland within the National Center of Competence in Research in Digital Fabrication, where, for example, I'm in the structural engineering side, so I don't know much of material science, I think. But when we are developing a technology, so we have to put, I think, the different constraints of different fields that often are a bit contradictory, and to come up with something. This is sometimes difficult, but I think it's maybe our only way, and also collaborate with the different institutions. So I think it should be a must in order to really push digital fabrication to make it real. Then in the next points, I will show a bit more the research we have been doing, and I'm organizing by the reinforcement technologies we have used. And I would like to point out first that I think the role of conventional reinforcement, I think it should be still like important in digital fabrication, in my opinion. But we should not think in the classical way of doing reinforcement, or I think if we have the digital fabrication of concrete, we should in parallel have this, keep in mind, I think, this digital reinforcement assemblies or other possibilities. Here you will see the in situ fabricator robot developed at DFAB, but this can do this double curve welded reinforcing mesh. And if we have these possibilities, we can think about, for example, in this technology, it's mesh mold. So we produce, I think, our freeform double curve mesh that is fine enough in order we can cast inside a special concrete mix that compacts well, but does not flow out of the mesh. And this leads to a quite interesting technology to build, I think, complex shapes. Here you can see the production of the mesh mold wall at the DFAB house. It is like a residence for research guests at EMPA near to Zurich. And here you see that the robot inserts like a continuous 6 millimeters reinforcement, and in perpendicular is welding suture segments. In the future, yeah, hopefully, I think it's not segments, but we can have continuous reinforcement in both directions. This allows us to have, I think here, you can see it, so it can be filled, this wall, without the necessity of a conventional form. Then we have other technologies, like smart dynamic casting is like robotically driven slip forming process, in which I think the concrete science is like a set on demand process. So it's an accelerated concrete. So then it enters the formwork in a fluid state, and it leaves the formwork when it starts hardening. So it can be safe, and also it can be carry the weight of the concrete on top. And there are like several formwork possibilities: rigid formwork that it's rotated on the left, or like formwork that can be deformed, like this case. And what about reinforcement? So not in all cases we can introduce a conventional reinforcement, but if we have still a simple enough shape in which we can have the reinforcement and slip the element around reinforcement, we can have, let's say, a conventional structure built in a digital manner. Here you can see that the casting in this technology is not like in 3D printing that from top, but we have flexibility to do it from the side. So this is compatible with having the reinforcement pre-installed. This is the slipping process with a high surface quality. This is the result of this DFAB house close to Zurich that I was mentioning. On the left are these smart dynamic casting facade mullions, and on the right you see this double curve mesh mold wall. And in this case, so we did not do, I think, prototype testing. It just, of course, we need to have a structural test to check that I think everything behaves as expected, or that we can explain it. Then I think Eggshell technology or other technologies derive from mesh mold, in the sense that I think we have a set on demand process that can be used to have this slipping minimum formwork, but also can be used to reduce the formwork pressure. And this allows us to have minimum formworks. That could be like here it's 3D printing plastic formwork, but it could be just a tension plastic foil. And here, this is another structure in which, because of the geometry, we could fit inside the 3D printed formwork the reinforcement, and then cast it in with this set on demand process that minimize the formwork pressure. There were a question in the Q&A regarding other presentations about, I think, these weak interfaces that other presenters have discussed. And I would like to introduce a bit more provocative point of view is, okay, is this always negative? Because I have to admit that from the durability, it's something to be figured out, because I think porosity higher, I think, in this weak, close to these weak interfaces. So it's to be figured out if, I think, if we have a conventional concrete with a crack width of 0.0 millimeters, is this better than having not cracks with the weak interface? I think certain things regarding of the durability of reinforcement that are still not clear. But if we have a look just from the mechanical point of view, having these weak interfaces in our concrete plus continuous reinforcement, because we need this, otherwise we will not have a concrete structure. These weak interfaces are helping us because can, I think, generate more cracks, a higher number of cracks. And you can see on the right, I think we have done some experiments that corroborate what we expect with simple mechanical models. I think when we have 3D printing with some reduced tensile strength in the interfaces, we have like 30–40% smaller crack spacing and smaller crack width. So thinking in, I think if we put minimum reinforcement to control cracking, maybe, I think if we have weak interfaces, we could even reduce the amount of minimum reinforcement. Because I think when we do conventional reinforced concrete design, so we don't take into account the tensile strength of concrete, or if we have tension. I think if we have shear, I think this will be, I think, interesting to see what is the effect of the weak interfaces. But if we have only direct tension, we should not be that concerned from the mechanical point of view. Then I think we have conventional reinforcement, but of course for more complex shapes, fiber reinforced concrete, I think it's also has a high potential. And we have implemented fiber reinforced concrete in several technologies in the concept that we call interlayer fiber reinforcement. What is this? So instead of placing the fibers in the concrete mix, if we are doing an additive manufacturing concrete process, why not to do a separate additive or just placing process for the fibers? So in this way, we 3D print like a layer, and then we place the fibers separately. And this has some benefits of, so we don't affect durability, or so we can use long fibers because we are not pumping the fibers, and we can grade the fibers and place them only when they are needed and in the orientation we want. And we are still, I think, working on this approach because it's not automated at the moment, and I think we have to figure out, I think if we put a lot of fibers in an interlayer, maybe we have some negative effect that we don't have if the fibers are mixed in the concrete. But we have applied the concept in this 3D printing of this 1.6 meter beams. What you see on the right, the cross section, and we applied, I think, this aligned interlayer fibers, and also we compare with this cable in the interlayer, similarly as done in Pua and Doben. But I think this was done manually. I think it's just a proof of concept. Then the longitudinal reinforcement was inserted and injected in the voids. Here you can see the results. So of course, I think when we add the fibers on the cable, so we managed to have a good post-cracking behavior. And then you see here in the crack pattern, we have like multiple shear cracks. So we were even able to break the cable, so we reached good bond of the cable. So this is promising, but I would like to conclude to a last approach that I think it's very interesting, is how knitted textiles will be used, I think, that are used for producing, I think, like t-shirts, or there are a lot of machines that can produce knitted textiles, or can we use this for construction? I think this has the benefit compared to, I think, this conventional woven fabrics that has been presented by other speakers today. But I think complex shapes can be done, I think, very easily. While I think in these woven fabrics, I think to do like the free-form shapes, we have to stitch multiple patches, so I think it's still quite labor. And this is the KnitCrete technology, so where we have this knitted textile that is tensioned, then cement paste coating is applied to have enough stiffness to cast on top concrete. And now we are working, I think, in order this knitted textile is not only loss formwork, but also works as reinforcement using like high strength fibers, aramid, carbon and glass fibers. So we are testing this with, I think, with direct tension. You see here on the left, and also with bending test. Here you very quickly can see the results. So I think when we have just the aramid knitted textile, then the behavior, I think we have some hardening, but it's not good, the behavior. But we can add also in this knitted textile some straight inlays that is giving really to some like behavior similar to traditional textile reinforced concrete. And also we are checking, I think, okay, what if we do a coating with cement paste or with more traditional epoxy? This seems to work better for glass fibers, I think, with this traditional epoxy. And final, I think we don't only want to see, I think, to build elements with this textile reinforcement that at the end has a brittle failure, but also our ambition will be to be able to integrate these features that allow us to, I think, integrate some channels for the reinforcement into the structures. And in this way, I think maybe we can use conventional reinforcing bars that do not have to be pre-bent, and then I think we insert inside the textile, and then this can be some like bending active elements that act, I think, as tensioning elements of the textile, but also as a final reinforcement. And I think this also have quite some potential for say elements and also beam elements. And so I talk about collaboration. So I would like to thank everyone that collaborates, I think, within these projects. And thank you very much for your attention. Here you have my email, so feel free to send me any question. Thank you.
Thank you very much, Jaime. I'm always impressed by the work of ETH, because actually you used the right word, so collaborative approach. So we need to get this opportunity to work together and face this multidisciplinary environment, because we need many expertise, and ETH is always approaching this problem in the right way. So thank you again.